We're busy looking at the cross product of vectors in R3. In the previous video, we defined the cross product and we looked at some properties, and we're going to continue with that. So let's look at two vectors, v and w, and we're looking for the cross product of v and w. Now the technique we used, we wrote I, j, and k. Yet again, if you're familiar with determinants of matrices, then you're finding a determinant. If not, we're just looking at the pattern. So we're writing v, we write w, and we see what happens. You might want to start looking at v and w and see if you can see a relationship there, but this links with one of the previous properties we looked at. So for the first entry, we ignore the first column. Minus 1 times minus 4 is 4. Minus 2 times 2, so it's 4 minus 4 is 0. Then we put a minus in front. We ignore the middle column, and it's 3 times minus 4, so it's minus 12. Minus 6 times 2, so minus 12, so it's minus 12 plus 12. That gives me 0. For the third entry, we ignore the third column, and we've got 3 times 2, minus 6. 6 minus 6 gives me 0. Remember, it's a vector, so we use the triangle brackets, so we've got 0, 0, 0. Right, now let's look at the two vectors v and w. Please notice that they're scalar multiples of each other, so we can say that w is minus 2 times v. So these vectors are parallel. Now what we said at the end of the previous video is the vectors are parallel, their cross product is 0, and we've seen an example here. It's not a proof, it's just an example. And the magnitude of the cross product is the area of the parallelogram between the two vectors. But if they're parallel, there's obviously no parallelogram that has an area. So here's an example of two vectors that are parallel, and their cross product is 0. All right, so let's look at these vectors. 2, 1, minus 4, 1, minus 4, 2. Question says determine the cross product and the area of the parallelogram. All right, so we know what we're supposed to do. So we're practicing cross product. I, j, k. 2, 1, minus 4. 1, minus 4, 2. So v cross w, ignore the first column, we've got 2 minus that product. Now that product gives me 16. So what we have is 2 minus 16 is minus 14. Then we put a minus in front of it because the definition says same pattern, just put a minus in front of it for that middle one. So we ignore the middle column, so it's 2 times 2 is 4. Minus 4, so it's 4 plus 4, so that's 8. And that minus comes from the definition. And then for the last entry, we ignore the last column, and it's 2 times minus 4, so it's minus 8. Minus 1 is minus 9. So there's the cross product. Now, yet again, we saw in the previous video that this cross product gives me a vector that's perpendicular to both of those. All right. But also that the norm of the cross product is the area of the parallelogram between v and w. So that's the square root of minus 14 squared plus minus 8 squared plus minus 9 squared, which is the square root of 341. You can calculate. And just please notice, we saw in the previous video that the cross product of w and v looks very similar to this one. It'll just be minus 1 times it, so it'll be 14, 8, and 9. So the area of the parallelogram will be exactly the same. Right, next example. Now we're looking at dot products with cross products. Now remember, we said that the cross product is perpendicular to both those vectors. So let's test it here. This is the same vectors we had in the previous example. So we already have the cross product. V cross w. We have as minus 14, minus 8, minus 9. So if I take the dot product of v with v cross w, so v is a vector, v cross w is a vector, we can take the dot product and we get a real number. So it's 2 times minus 14, which is minus 28. Minus 8 times 1 is minus 8. Minus 4 times minus 9, so it's plus 36. And that gives me 0. Again, this is the 0 number, not a vector. W's dot product with the cross product is 1 times minus 14 is minus 14. Minus 4 times minus 8 is plus 32. 2 times minus 9 is minus 18. So that also gives me minus 20 minus 32 plus 32 is 0. So as we said, that cross product, V cross W and W cross V, is perpendicular to both V and to W. Now remember, when we looked at properties of dot product, we said we've got, if the dot product of two vectors is 0, the vectors are perpendicular. So this is going to come in handy when we look at the next section on what we can use the cross product and the dot product for further. So just some properties. We've seen W cross V is minus 1 V cross W. So it's not commutative, the cross product. But if I've got a scalar multiple, lambda times V cross product with W is lambda times V cross product with W and V times lambda W. Right. Yet again, we're not going to prove these, but they can be proven using the definitions of scalar multiplication and cross product. And then we've got a distributive property. Use cross product with V plus W is use cross product with V plus use cross product with W. So that is the cross product. In the next two videos, we're going to look at equations of planes, and we use dot and cross products to help us find equations of planes in 3 dimensions.